All right, y'all. Welcome back. We are looking at section 2.1 on matrix operations. Um, so in general, when you're looking at an m by n matrix, we can think about each of the individual entries in terms of their row and their column. So first row, first column is A sub 1, 1. The first number is the row, because the same way that we refer to m by n matrices as the rows by the columns, that's how their subscripts work too, which is nice. It's consistent. Consistent. So we have our matrix big A, and it has entries A sub ij based on the ith row and the jth column. And all the dot dot dots mean that we didn't forget anything in between. Sometimes you see diagonal dot dot dots, which is always fun. I like them, and if you're interested in looking at how to do those in Overleaf in LaTeX or whatever, have fun with that. Some other things, so we have, this is our matrix. Our main diagonal are whenever I equals j. So that's our main diagonal. That's just straight down like if we're thinking of this as a box, our main diagonal is going from there, and this, of course, is for a square matrix, which you can have your A sub I j entries where you make sure that your I equals your j, and that's your main diagonal. A zero matrix is where you have a matrix of all zeros. A diagonal matrix is where you have only numbers that are non-zero on your main diagonal. So like our identity matrix is one example of a diagonal matrix, but I mean, like, you could also have your main diagonals like 7, 5, 2, and then you got zeros other places. There's not a ton of information in that matrix, but it is a matrix nonetheless. And sparseness is also something that we can measure in terms of matrices, and that's how some analysis happens. So that's pretty interesting. If you want to think about that more, then go right ahead. But in MATLAB, you can also make a diagonal matrix by typing in diag and then putting in a vector, and it'll make a matrix like this, where you have zeros everywhere except for that diagonal that has entries of your vector. If you want to make matrix of zeros, then you put zeros and then the size of the square matrix of zeros that you want. All right, so more on MATLAB. Think about what would happen if you had these matrices. So you have A, B, and C. Can you add them all to? Can you add A and B together? And from here you can kind of see, and it's kind of nice that the way that those look, they like line up this way, right? So then your entries, they line up very nicely, but you could also write them 4, 0, 5, negative 1, 3, 2, plus 1, 1, 1, 3, 5, 7. And you can see that those are the same size, so we can add them up. We can do that addition operation. And what do we get? Wow. 5, 1, 6, 2, 8, 9. Just adding up the corresponding entries into those locations where they have the same subscripts. So this is like A11 plus B11. For C, A and C, we don't have, we can't add them together because we don't have corresponding entries for everything. Because we're missing a column on C. C's 2 by 2, whereas A is a 2 by 3. So we're missing a column on C. We can't do anything with that because you can't just make up things or just say that it's nothing, because there's no information, so you can't say it's 0. So we can't do A plus C. A little sad face for that. We can scale, so we can scale up our B. So all of our entries for B, we can just multiply by 2, and that's what's going to happen for our scalar, where our first row is going to be 2, 2, 2, and then our second row is going to be, what, 6, 10, 14? Yeah, scale everything up by 2. And we can also take A and then subtract the scalar multiple of B. So if we have this matrix A, which I guess I will circle here. This is matrix A minus matrix B, 2 times matrix B. Then what are we ending up with? A minus 2B. This is going to be 2, negative 2, 3, negative 7, negative 7, negative 7, just kidding, negative 12. So we can do operations. Lovely. But the only time we can do operations is whenever we have corresponding entries. So if we don't have the right number of entries, we can't do addition or subtraction. Subtraction is just scalar multiplication with a negative 1 and addition. It's secretly the same. Yep. You can plug these into MATLAB. These are the format that MATLAB likes. It doesn't understand that 2b is going to be multiplication, so MATLAB is not smart in that way, but that's okay because you're smart, so you can put in the star for the multiplication. And then if you're interested in suppressing output, I don't know if I mentioned this before, but you can put a semicolon after that line and it won't print it out, so that really helps for when you have giant things to deal with and you don't want to have like a huge printout of like a 50 by 50 matrix, because that's too much. Alright. So we have matrices that are the right size, the same size, and we have scalars. We have the commutative property of addition, associative property of addition. We got the identity property of addition, so that's nice. Scalars can distribute. We can also distribute our matrix because we're looking at a sum of scalars. That's nice. And then our multiplication with scalars, we can also group those as well. Which of these is more efficient in terms of like computation? It's an interesting question. Alright, so if we have an m by n matrix and an n by p matrix, so they're different sizes, then we can multiply, which is so cool. And our product is going to be our columns, which are our vectors, our columns of B as vectors, with our matrix A multiplied by each of those. So because we know how to do like AX, I'm not sure if I'm that. We do know how to, like A times a vector X, right? We can do that. So we're just taking multiplication of our matrix and we're representing it in a way that we know before. We're taking our matrix A multiplied by some vector B, and we're doing that for each of our columns for B. And so what size is our matrix going to end up being? We're going to have matrix A times this n by 1 vector, and so we're going to end up with an m by p matrix at the end of it. Alright, so each column of AB here is a linear combination of our columns of A using weights from the corresponding column of B, so these weights that we have for our columns. So let's compute. Will this work? This is a 2 by 2, and this is a 2 by 3. So can we have corresponding weights? Weights from corresponding columns of B. Do we have the right number of weights? Yes, I think we do. All right, let's do it. So we have 2, 3, 1, negative 5, and then we're multiplying that by our columns. 4, 1, 3, negative 2, and 6, 3. So what do we get? We got 2, 3, 1, negative 5 times 4, 1. And then we have 2, 3, 1, negative 5 times 3, negative 2. And we have 2, 3, 1, negative 5 times 6, 3. Wow, how tedious. Alright, let's do it anyway. Okay, so we get 8 plus 3 is 11. 4 minus 5 is negative 1. 3 times 2 minus 2 times 3 is 0. 3 plus 10 is 13. And 6 times 2 plus 3 times 3 is 12 plus 9 is 18. No, 12 plus 9 is 21. And 6 minus 15 is negative 9. All right. Hope that's right. Let me check it. So I checked it in MATLAB. So I put in A and B, and then I had A times B, and then I clicked the publish button. Publish is really nice because then it gets you what you had typed in and your outputs. I guess we could have suppressed these with semicolons, but that's okay. And then we ended up with 11, 0, 21, negative 1, 13, negative 9. Yes. Okay, so if we have A is 3 by 5 and B is 5 by 2, what size is AB going to be? AB is going to be 3 by 2 because we have the inside numbers matching. Is BA going to be defined where we have 5 by 2 times a 3 by 5? Nope, we do not have matching inner numbers because we don't have the right number of entries in our column vector that will fit our rows and our other matrix. So BA is not defined. Can't spell defined. Ba is not defined. If we do know that AB is defined, then our entry in row I and column J of AB is the sum of the products of our corresponding entries for row I of column A and column J of B. So where you have A has a row I and B has a column J. And if AB sub IJ denotes the ijth entry of our product AB, then we have AB sub IJ is going to be the sum of these products. The sum of these products where our inner number matches and indexes up. But our I for A row and B for J's column do not change. So our row sub I of our product AB is our row sub I of A times our entire matrix B. So if we have A as an m by n matrix, so it's not necessarily square, and we have B and C that are sizes that work. So we need sizes that work such that these are going to be defined. Then we have associative multiplication, which is nice. We have the distributive property on the right and the left, which is also nice, but this is misleading because right is not the same as left in multiplication. So that's misleading, but keep this just like in your mind that this still works, but right is not the same as left. We have scalar multiplication, and that works for any of our scalars, and multiplying by our identity matrix, as long as that identity matrix is the right size, doesn't change the value. That's why it's the identity matrix. So in general, we don't have commutativity for multiplication. We can't say that if AB equals AC, that implies that B equals C. You're going to work on that in your problem set. And then you also you don't have the zero product property, essentially. if you have A, B is our zero matrix, you can't say that A or B is equal to our zero vector or a zero matrix because there's other ways that things can cancel out. So not all of the properties that you know and love are relevant for matrix multiplication, but some of them are. Nice. All right. So we're just gonna verify that this is not commutative. So try to multiply A times B and B times A and see what you get. So we can show this using MATLAB again. So we have A and B that we entered in, and we have A times B and B times A, and look, they are not the same. We verified it. Good job, everyone. So we can also have powers of matrices where we multiply repeatedly, and this is only going to work when we have our dimensions line up. So that means that we need to have square matrices for our powers. Because if you think about it, if like m is not equal to n, then you have an m by n matrix multiplied by an m by n matrix. Our inner numbers don't work, and so they're not the same. And so you don't have, you can't have that matrix multiplied by itself. In that way, you would have to do like a transpose or something, but then how would you toggle the transposing? Wow, so much. So this powers a to the k power only works when you have an n by n matrix. Speaking of transposes, when we have a matrix and then we take the transpose of it, you just take the entries that are not on your main diagonal and you swap where they are. And also, so an m by n matrix, when you transpose it, and transpose, some people use like the capital T superscript, which you can also use transpose like this, which is your little apostrophe in MATLAB. And so when you transpose that, you end up with an n by m matrix. So our main diagonal stays the same, AD, right? Those stay the same, or -5, -3, -5, -3, those stay the same. But then our other entries swap around. So B goes down there, C swaps up here, and for this, our 0 goes up there, our 1 goes over here, and so on. Our 2 is there. So you see the swapping of those positions. And another way that you could write that is when you have A has like a ijth entry. In A transpose, that's going to go to the jith entry, where you're swapping your row and your column. So suppose that we had A and B are matrices whose size works. Then if you take the transpose of the transpose, you end up with the same thing, right? Transpose, transpose, you undid the transposing that you had, so that is just going to work that way. If you have the sum of A, B, and then you transpose it, you can break or you can like effectively distribute out your transposing, because you have A, B that are the right sizes to add them together, so you can transpose them and add them together, and then it'll still work. Your scalar isn't affected by the transposes because your scalar is being multiplied by everything inside your matrix. It doesn't matter where those entries are, so you can just factor out your scalar like that. And if you're taking your product and then transposing that, then that is going to result in the transpose of B times the transpose of A. So you're reversing your order, the reverse order for that. So think about how you could prove that. And just one last thing is how would a computer obtain A times B? Like, what would a computer need to do in order to find that product? What would the best way be? And does it depend on what kind of computer system you're looking at? How much memory does it take? So those are some questions that I'll leave you with. I probably won't answer, but you can answer in a journal. It'll be great. All right. So what did we look at? We don't have commutativity for multiplying matrices. The dimensions need to match up. We still have addition and identity stuff. really well. Like those work, those are nice. And we have matrix multiplication is back again to the idea of linear combinations and having weights. That's one way to think about it. And MATLAB is really helpful. All right, that about does it. Bye.